What observations did you guys come up with? What do you got, Ellie?
It has 2 eyes, 1 nose, and 2 ears.
Damn. Okay, I'm just going to pick the 2 eyes. Where do you want to place that? Qualitative or quantitative?
I would say quantitative.
Okay, so by specifying the 2, you're now saying quantitative. We won't quite get into the definition of those yet, but I'm okay with that. Anthony, you got a hand too?
Got a thick coat of wool.
What do you think? Qualitative, quantitative? What else?
It has 2 cheeks.
You're leaning down.
Qualitative, quantitative?
Qualitative.
It's like it's missing a tag when it's left ear. There's a hole there.
I've wondered about that too. Like, is that an image flaw?
No, there's supposed
But
to be a tag.
I think there is supposed to be a tag there. What do you have?
Surrounded by nature.
Or green leaves.
You can only see 2 of the legs.
Any farmers? Okay, I'm going to add one. But I was told that that's roughly what that sheep looks like, just for the record. What's that?
Wet or dry.
Why?
Huh?
How do you get the 107?
So someone that works with sheep took an approximation based off of what the average sheep
Like
looks
one of
like
your
and
classes.
what that looked like, yeah, and said it's actually about 170 pounds. Yeah, yeah. It's better than the guesses I've thrown out. Like, I try and pick other units so that it obscures the fact that I have no idea what I'm talking about when it comes to the weight of a sheep. Okay, so there's a bunch of observations. Which one's the most important?
Qualitative.
Depends on what you want.
Depends on what you're trying to
This is one of the big issues within science, okay, as well. When we talk about observations, we have 2 different kind of classifications, qualitative and quantitative. Okay? Depending on the context, it makes a really big difference which one you might care about. For instance, if the context is, I'm a butcher, do I care? I might care about the surrounded by nature, right? Like, free range versus penned. Okay. Do I really care that it has a thick coat?
No.
Probably not. Okay. It might say something to the health, but the biggest concern I'm going to see with that as a butcher is that it's a 170-pound sheep, and I can get, and I asked the guy about this too, I think he said 90 pounds worth of sellable meat. Okay.
That was a good point.
So that's based off of that quantitative observation. Okay? But what if instead of being a butcher, I'm instead a, there's got to be a tailor. I'm going to want the qualitative. I'm going to want to know what the wool is. Okay? What is the quality of that wool? So the context by which we look at or make observations can change the level of importance for what we're trying to do. Right? And that's a really big thing to recognize and to value. When we go through and do an experiment, typically what are you being asked to record? Data. Well, what's your data? Data is ultimately an observation. Numbers. So if we think about science as a whole, we're typically quantifying, we tend to be looking at the quantitative results. Okay? Are the qualitative then not important?
No.
No, they are incredibly important, and we could go to those qualitative observations to say that the experiment failed because the water I was using was black. Water's not supposed to be black. Okay? That's why my experiment failed. Okay? There's some unknown impurity in that. I have to deal with that variable. So a lot of the variables that we're trying to control, things that we're trying to understand and limit so that we can learn something from an experiment, okay, happen in that qualitative realm. Quantitative is relatively straightforward. That's using usually a device to take a measurement. Okay? So when we look at the pounds, there's a balance that we use to measure that. When we look at the quantifying eyes, that one gets a little bit weird. We are using a device sort of to make that measurement. What was that device?
Our vision.
Our vision. Okay? We use vision in the qualitative as well. Okay? But what we tend to observe for our quantitative is we try to really lock down and make it as objective as possible and get away from vision. Okay? One of the observations kind of came up, green leaves. Really, are they actually green or are they lime green? Are they mint green? Are they olive green? Okay? Those subtle variations can be very difficult to quantify and make consistent from person or experimenter to experimenter. But those types of observations can really help lend us some clues as to why things worked or did not work. Okay? So a lot of the origin of science came from looking at the qualitative and making those observations and then saying, well, we've lost some definitions, so let's start to quantify. Let's build instruments to quantify these things to make it more objective. Kind of make sense? Okay, so let's start with the qualitative. 70-80% of life is... You learned that one yet? What is 70-80% composition of life?
Water.
And the planet. It's water. Right? Water is an interesting substance. Why would water be an interesting substance to start our observations with? It makes up everything, so that's a good reason. What else? Say that again?
We need it.
We need it.
Changes a lot.
What do you mean it changes a lot? And yes.
Like ice.
So it could be ice or steam or water. I like where you're going with that, but those are now specific to the substance of water. How can we take a step back from that? You guys have something?
It's a
Solid?
solvent.
You got solvent too, that's typically liquid. So you have liquids, solids,
Gas.
and gases. Water is one of the few substances that we can find all three of those phases readily available. Right? So subtle changes in our environment allow us to observe water as both a solid, a liquid, and as a gas. Being able to identify and see those different transitions can help us to qualify the different phases of matter. Okay? Can most phases or most substances transition between all of those? Yeah, given the right circumstances. Those circumstances can be very difficult to achieve. Okay? For instance, I can get liquid iron. Right? That happens. Is that something that's going to be easy to get? No. Okay? We would have to scale up significantly our abilities to generate enough heat to cause that transition. Okay? There are other things that don't transition smoothly between those phases, and we get other issues that pop in. So water is neat because we can make observations about each of those. So let's take a swing at the three pictures I've got here to identify which phase you think we're representing. Which one's which?
Solid as snow.
Solid as snow, which I know there's a questionable image in there. Which one do you think is the solid? Left, top? Top left is where I'm aiming for that. That's our solid, followed by
Liquid is the liquid on the bottom.
liquid's the bottom,
And then gas on the right.
and then gas is the attempt at boiling. Okay? And we can see why gases might be difficult to quantify because we can't really see them. We can see the result of them forming bubbles in our liquid, but we don't see the gas cleanly. Okay? There was a hand? What do you got?
Wait, so on the bottom picture, is like the lake solid or like is it frozen or not?
It's not supposed to be frozen.
Oh, okay.
This is what happens when you build a slide really quickly and then decide it's good enough.
I mean, there's a boat in it.
There is a boat there.
You could
That's supposed to be a lake. So, yeah, I think I found some other pictures that they were like, look at how clean this water is, so that you couldn't actually see that there was water. I was like, that doesn't really work either. So, three main things we can go through to identify shape, volume, and compressibility. So let's kind of think through what we would expect. Okay, so our solid going straight down, liquid's going up, gas is going down. What do you think about shape when you think about solid?
Block of ice.
Okay, a block of ice. Okay, if I have that block of ice, maintain a constant cold temperature so that we keep the block of ice. Don't start changing phases on it. What happens to the shape?
Stays the same.
Stays the same. So our shape, okay, is constant. What happens when I look at the shape for the liquid? It does move, right? Okay, if I just took the liquid water and poured it on the table or put it on the table, it's going to spread out. Okay, so our shape is variable. Shape for the gas?
Variable.
Extremely variable. Okay. How about volume?
Solid states.
If the shape never changed, what's going to happen with the volume?
Stays the same.
Constant.
It should also be constant. Okay, how about for the liquid?
Should be constant.
Okay, it is also constant. Even though the shape changed, it's still occupying the same volume of a different shape. Okay, so it's still the same volume. And the gas?
Variable.
Also variable. Okay, depending on the shape of the container, that's going to be the shape of the gas. Okay, with just that information, could we start to come up with a model for what a solid might look like? Okay, versus a liquid versus a gas. Okay, so let's start it off. Here's a solid particle 1. If I now have a solid, I'm going to have a lot of those particles. Where would I draw those other particles?
Same as
Right next to it.
Okay, right next to it. What if I did that with the liquid?
Spread out a little bit.
Okay, spread out, an interesting word there, nice qualitative observation, a little bit. Okay? They're going to have a little bit more motion. So what we might try and do is drop in a container just to see how they're going to occupy. So we're not getting the same shape that we saw in the other case. It's going to change based off of that shape. Okay? What happens if we move to the gas?
Particles are going to kind of be apart.
Particle space is now going to be much larger, okay, in between. Okay, that was largely just based off of looking at shape and volume. Notice I had to close the container for the gas. What happens if we now go look at compressibility? To compress, what must change? The space between those individual particles. So let's take a look at the solid. There's hardly any space there. Okay? For those of you being like, there's a little bit, there is a little bit, and there is a small amount of compressibility. And depending on the substances, you can get varying amounts. But for the most part, as a general pattern, solids aren't compressible. Okay, what about liquids?
Very.
To a point.
A little bit. There's a little bit of compressibility. It's certainly more than the solid, but they're still pretty closely packed to each other. Okay? And you could say, well, I can push in one point and my finger goes through. Well, what's happening? Displacement, not compression. Displacement. All you've done is move those particles. Okay? So when we look at the compressibility, it's also pretty darn close to none. When we look at the gas, there's a lot of compressibility. Okay, so it is very compressible. So all we're trying to do is make some of those qualitative observations, and those simple qualitative observations allow us to now define things as solids, liquids, and gases because of those differences. We kind of looked at it in the reverse. Here's a solid, a liquid, and a gas. What would those observations be? Make sense?
I thought you could compress gas.
You
It's
could-
like if you have it on a syringe, you can't press it if it is sealed.
So, and there's an interesting observation. If you put gas into a syringe, okay, and you seal that, you can't compress it. You may not be able to compress it, but somebody can. Okay? You can absolutely compress it, and that's going to come down to how much pressure you put behind it. One of the things that's going to happen is as we compress it, what happens to the space between those particles?
It's smaller.
It gets smaller, which means as we compress it, what starts to happen?
It will become a liquid.
It will phase transition. Okay? So this is why if you've seen butane lighters, like the clear ones, you can see the liquid in the side, right? You're going to say, oh, there's how much stuff is there? And they've got a bunch of liquid in there. And then when you go and light them, you don't see any liquid come spraying out. Okay? That container was pressurized. It had enough pressure to force a phase transition to the liquid. When you release the trigger and let it out, what happened to all that pressure? It goes away, which then means it phase transitions up to the gas, which is great for a butane lighter, because then what can you do? Light a spark, you maximize surface area, and you can get a fire right away. Okay? So we can transition between those by changing certain things. Pressure's a really big one. Okay? What else could we use to transition between them? Temperature. Okay? As we move through, we will look at pressure, but much later in the semester. The temperature one is kind of a more relevant one, I guess, for the majority of the semester, because it's a little bit easier to manipulate. Pressure can become sometimes questionable. Okay? So now we've got solids, liquids, and gases. We want to further be able to categorize these. So all matter is going to be made up of a solid, liquid, or gas. And now we say, well, how can I combine those solids, liquids, and gases? Okay, what are the results of those? So the first kind of differentiator, for lack of a better descriptor, mixture versus pure substances. Okay? I do have, full disclosure, issues with some of these definitions. So we'll have to use kind of examples to address them. Mixture, spatially linked. Okay? This analogy actually seemed to work fairly well in class for the standalone, so we'll use it here. Okay? So I'm going to stand next to John, right? Here I am, right? Are we spatially linked or chemically linked?
Spatially.
Okay, spatially. Okay? So that one's not a big deal. We tend to be spatially linked with a lot of things around us. Okay? So what makes it more difficult is when we move to the chemical scale, we're looking at an abstract particle that we can't see, and that becomes challenging. Okay? But we have ways to represent that. So let's flip it and look at a pure substance. Okay? That's now chemically linked. John and I were chemically linked. Might be a little weird, right? Okay? So let's look at a chemical linkage. Okay? Instead of referencing John, I'm going to reference my arm. Let's say my arm was spatially linked to my body. What might you expect to potentially happen? My arm could just fall off. Okay? Okay? To answer questions, all you got to do is take your arm off and throw it at the instructor. Now they know, because they literally have your arm, and they go, it must be your question. Okay? It's like passing the baton to ask questions, right? Okay? You just got to get your arm back.
The next zombie movie.
Yeah. Okay? That's our difference, really, between chemically linked and spatially linked. The chemically linked is not an easy thing to break off. Okay? If my arm just fell off, or if I took my arm and threw it at you right now, you would probably be freaking out. And not just because you had a 20-pound arm flying at you. Okay? How did that arm all of a sudden just come off? Okay? So that's our kind of differentiation between chemically linked and spatially linked. Chemically is questionable. Okay? And I don't like referencing it as chemically linked, but that's what we've got to work with. Why might I have a problem with calling it chemically linked?
Where are the chemicals?
Okay? You're in what class? Chemistry. Which level of chemistry are you in?
Fundamental.
Fundamental. You mean the very first chemistry class. You have zero chemistry experience, and second day of class, I'm defining a word by using a word you've never learned, that you're actually taking a class to learn. That's a very sketchy thing to go through and do, in my opinion. Okay, we will continue to dig into that, but that example with the arm, zombie arm, seems to work fairly well.
So when it talks about chemically linked, does that mean like types of bonds it has? Or
It is going to address something with bonds, but again, we're using a word that not everybody knows. Okay, so how could we represent this? Okay, how could we represent when we're looking at spatially linked versus chemically linked atoms? Okay? And atoms in and of itself is actually a topic we haven't even got to. But let's try what you guys already know. Formula for water.
H2O.
Okay. Okay. So H2O. Is the H chemically linked to the O?
Yes.
Yeah.
How about now?
No. The oxygen isn't, but the two hydrogen are.
Okay. Is the hydrogen chemically linked to the oxygen now?
No.
Why all of a sudden no? Like some people over here, it looked like
It looks spatially.
you're now saying spatially, and you guys are saying it's not chemically. What changed?
Separation.
The space between the atoms. So when we talk about units of meaning in Greg's class, this is what we're looking at. There's a unit of meaning that wasn't actually written. That unit of meaning was how large is that space? Okay? If it's large enough, they're not chemically linked. They're now spatially linked. If it's small enough, they're now chemically linked. Okay? Are they chemically linked now? That line is very difficult to nuance. Okay? So as chemists, we try to clarify that as much as possible. So if we're looking at just water, that becomes a little bit more difficult. Okay? And we might try and write that as close as possible. Okay? Not overlapping, because then it becomes confusing. So we're kind of following the standards of different words in English. Right? That's kind of confusing. So what did we do?
Space.
Printing.
So the same norms that we use to differentiate words in English, we're using in chemistry to differentiate chemically versus spatially linked. Kind of make sense?
And the writing principle or language principle is called morphology. We'll get to
So, because Greg mumbled it in the back of the classroom, for those of you actually watching at home, would be morphology. Okay? So, let's nuance out mixture. Okay? When we look at mixture, that really divides into two categories, heterogeneous and homogeneous. Okay? Kind of hard to use examples, but we're going to try again. Sorry, I didn't mean to hit your computer.
You're fine.
Okay? I'm going to have a mixture now with John. And a mixture with Rose.
I don't know if that sounds really
Okay?
complicated.
Hetero, homo. What are we looking at? Okay, in our descriptions, these are visible separation versus no visible separation. Can you visibly see that we are separated? Yes, so that makes the visible separation difficult. So use what language you have access to. Which is heterogeneous?
This is a little, like,
Well, right now, am I in a heterogeneous relation?
oh, I thought you meant
Mixture? Dang it.
Yes.
Or a homogeneous mixture?
For them behind us, it'd be a homogeneous because they can't see the separation.
like walking to them or like.
No, here's mixture 1.
Oh, okay. All right. Yeah.
Here's mixture 2.
It depends on the view.
So some of it can depend on the view. Let's use the biggest viewpoint we can right now. This mixture right now would be heterogeneous. Why?
Two different
Because
types.
it's visible.
2 different types. Okay? So he and I are the same type?
Both males.
Okay? So we're classifying based off of what we have access to. Okay? We're saying male, 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 female. We can see that differentiation. Sometimes those differentiations aren't easy to see. Okay? And it makes it a lot more difficult to make those classifications. that doesn't mean we don't attempt to make those classifications. One of the things that becomes difficult is we start to make those classifications and then add judgments on top of that. Science is not supposed to be judging, it's just supposed to be making the classifications. And that's where scientists can get into a lot of trouble. They're just like, oh, we just see the distinction, that's the way it is, without taking into consideration other aspects. Okay? So when we go through and look at it at the chemical level, what is that visible separation? Right? Because you already have the tools to identify what we're separating in chemistry.
The two different elements?
Two different elements. Water. Is water a mixture or pure substance? Is hydrogen spatially linked to oxygen or chemically linked? It was chemically linked, which means water is a pure substance. I didn't even get that far yet. I know where you're going, but don't do it yet. That means water is a pure substance, not a mixture. If water is not a mixture, it's not homogeneous or heterogeneous. Okay? So what tools do we have to be able to classify that separation? What are we separating away from?
The periodic table, like the base part of the periodic table.
Okay, periodic table is not a horrible idea, but have I officially talked about that yet?
No.
No, so I don't like it. What have I defined for matter?
Mixture of pure substance.
16.
Would it be, if we want to each?
16. That's my hint. 16. You want another hint?
Sync.
17.
Numbers.
The qualitative observations.
What were our qualitative observations literally on the last slide? What did we observe?
Those states.
The states: solid, liquid, gas. Visible separation or no visible separation between the states. So if I add sand into water, sand is what phase? A solid. Water is liquid. When I put those two together, that is by definition a mixture. Is that a heterogeneous mixture or a homogeneous mixture? Heterogeneous. Why? You can see the difference in phases between solid and liquid. Okay? Oil, what phase?
Liquid.
Liquid. Water, what phase? Liquid. I mix oil and water. What do I get?
Homogeneous.
Homogeneous.
You can see
No, it's a heterogeneous.
Because they don't mix.
Okay. In our mixture there, okay, for those of you that may be a little bit vague with those terms, salad dressing, and not like the store salad dressing, like you make your own salad dressing, like vinegar and olive oil, okay, or water and olive oil, you see a clear separation between those. Yes, they are both liquids, but is there a clear, visible difference between those two liquids? Yes. That makes it heterogeneous. Even though both phases are liquid, there's still a clear separation between them.
So like a homogeneous mixture would be like mixing food dye with water.
Okay? So what if we take colored food dye and put it into water? Right?
You can see it initially.
When we first put it in, and that's one of the extra things. Well, when I first put it in, I can very clearly see that difference. What we're talking about is not the very initial part or the mixing process. We're talking about a steady state. So once it has been fully attempted to mix, okay, and we just say, okay, now chill for a little bit, does it separate back out? No, which means homogeneous. Okay, let's throw another curve in there, just because I think this is fun. Let's take table salt, sodium chloride, which is what phase? Solid. And let's take water, which is what phase? Liquid. What happens when I mix those two? Okay, I get salt water. Okay, homogeneous or heterogeneous? Homogeneous. We can't differentiate them. What phase do I have? liquid, solid, liquid, gas are all in direct reference to pure substances. It's not pure. Those are now mixtures. That's a spatially linked system. So I can't call this a liquid or a solid. So I would need a new descriptor of that new system that references our mixture, and in particular, our mixture dissolved in water. If you were, say, to be thirsty, and you didn't have a water bottle, you might go up to a machine, right? Like the soda machines, but you wanted water. Don't buy that soda crap. You might buy a particular brand of water. Any guesses? Dasani. Doesn't work for me. Thank you. Aquafina. Aquafina meaning?
Water.
Aqua, water, fina,
Filter.
fine or filtered, clean water, effectively. Okay? What's the new phase? It's referencing something dissolved in water. We can't say something dissolved in water because there's too many words. We call it aqueous. Okay? Aqueous is not technically a phase because our phases are typically classified purely with our pure substances. But aqueous is this weird kind of mixture phase. Okay? And we will hear reference to aqueous and see it show up typically as AQ. Why AQ and not write it out as aqueous? We're inherently lazy people. Okay? So we want that abbreviation. Okay? Should we throw on a real curveball? Sure, why not? Okay? Doesn't happen too often, but it happened actually a little bit, I think, over winter break. Fog. Is that a question or you already have an answer? Okay, let's do your question.
Aqueous is only related to liquid and solid?
Aqueous is specifically referencing a substance dissolved in water. So it could be a solid that's dissolved in water. It could be a liquid. It could be a gas. Okay, but it has to be a substance dissolved in water, and in particular, it's referencing the homogeneous system. Because if it was heterogeneous, it would be the liquid of water and whatever that extra phase was.
In a substance dissolved in specifically water or in a liquid?
Specifically water. Remember Aquafina. If you went to buy Aquafina and it wasn't water, but it was ethanol, there might be a problem. Okay, so it is specifically water.
Wait, so I don't know if this makes sense, but say like you're trying to like dissolve, for example, some substance that doesn't dissolve in water. Can you use like heat to make it dissolve, or?
I know where you're going with that, which is really cool, but we aren't there yet. Okay, so yes, we can change the properties of materials by changing conditions to force certain things to happen. What we're trying to look at is not the force, the base level first. Okay, so let's take a look at fog. What do you guys think? Hetero or homo? Okay, it's not going to be a pure substance. Okay, because fog is naturally going to be air, and what's in air? Oxygen, nitrogen, carbon dioxide. None of those are chemically linked to each other. They're all spatially tied. So the instant we're looking at fog, we're looking at air. Air is already a mixture.
Homogeneous.
Okay? Homogeneous. Okay? Why homogeneous?
Because there's no visible spacing between the nitrogen and oxygen.
No. So nitrogen and oxygen, sure, that could work for standard air. That's like the air in this room. Fog's a little bit different. If this room was filled with fog, what would you see? It would be very difficult to see, right? Okay. Do you see a physical separation between the fog and not fog air?
You can.
But if the whole room is foggy.
It just looks cloudy. Like if the whole room was filled with fog, it's just fog, which would suggest homogeneous, right? Okay. What happens to your visibility in fog? It decreases. Why is it decreased? Why is it thick? What's happening? It has to do with light. Light is trying to pass through it. Okay? What is it encountering as it tries to pass through the fog?
Liquid water.
Liquid water. What's in the air? That's just a gas. If it's hitting a liquid, what do we have? We have a liquid and
A gas.
a gas, which means
Heterogeneous.
multi-phases, heterogeneous. Okay? Remember how we said that whole eye visibility thing can be a bit tricky?
So you're saying fog is heterogeneous?
It's heterogeneous.
Okay.
Yep.
That's where you went to go. Okay.
Yep.
Because there's a
Right.
visible
And
separation, but.
what I want you to recognize is how difficult it is to nuance that. Okay? To really differentiate that, we aren't just looking at it to observe it. We're observing how light is interacting with it to make our conclusions. Okay?
It's gonna be a test question.
No, I don't ask that level
Okay.
because that's it's pushing realms and it pushes experience, particularly for people in Arizona. Because how many people have actually experienced fog if you've just lived in this state? Let's assume 24 years. You've seen fog maybe once a year. The experience of actually dealing with fog and interacting with it, for instance, while driving, okay, high beams are going to be pretty limited. Okay, so when we ask questions on exams, and this is something that becomes difficult, particularly for me personally when it deals with exams, is you have to be careful asking questions about real-world applications, because if you haven't had that real-world application, that doesn't work. Okay? Some of the common ones like Kool-Aid, a lot of people have experienced Kool-Aid, so Kool-Aid's usually a safe bet, but if we reference Tang, we're like, what the hell is Tang? It's the same thing as Kool-Aid, but it's orange. Okay? It's the same process. So if you don't understand that distinction, that's going to be more difficult to nuance those questions. So I try to be careful with the real world questions on exams. That doesn't mean I won't throw them into lecture.
Okay. So
Okay.
by visible, do you mean like the naked eye or like?
It's a qualitative observation, and because it is qualitative, by nature it becomes difficult to nuance the exact line. You do have to be a little bit careful with that. If we move over to the pure substances, I tend to think these are a little bit easier to qualify. Okay, chemically linked. How did we notate they were chemically linked? They were written close to each other, which becomes interesting because if I tell you the formula for ethanol, or if I just say C2H3O2,
Is that it?
no, I actually butchered that horribly in that reference, but thanks for calling me out on it. Okay, we'll switch it up, C2H5OH. Okay, was there a space between the letters? I paused, but why did I pause? Was it to put in a space, or was it a thought that I had to make sure I got the formula right? Okay, so the verbal language makes it more difficult to translate our pure substances because our chemically linked versus spatially linked is all due to the spacing of the written language. So we have to be a lot more careful about how we reference those compounds and think about them. Okay, so chemically linked, written down, spatially very close to each other, okay, in a formula. When we move into differentiating that, we can get compounds and elements as pure substances. Okay, so for instance, if I looked at a compound of just sodium metal, you might see something written like this. Does anybody want to make the joke as I did it? Batman, thank you. Okay.
Oh, I get it.
Yeah. Is this a compound?
No.
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 I need at least two elements. I don't have two elements, which means it's just an element. They are a pure substance because the spacing between those is all very small. Make sense? Okay. What if I... What do we have now?
Compound.
Okay. I have multiple molecules that are spatially linked, but each of them are individually chemically linked. Okay? So we are a pure substance of water. It's going to be a compound because each of those pure substances have at least 2 elements within them. Kind of make sense? Okay. And then the one curveball I can throw out for this one. What do we all need to live? A formula for oxygen.
O2.
What do you think?
Element.
Why do you say compound? There are at least 2 elements, and this is where language can be a bit of a SOB here. At least 2 different elements. Because they're the same element, we'll refer to them as elements, not compounds.
Well, wouldn't you write it? You'd have to write it twice too, right? If it was a compound. It's like, wouldn't you do like O?
What you're then getting at is how could we represent that individual symbol? And there are multiple ways we could represent it. It's not going to change its identity. So I could have just as easily written that as that. Don't stress about what all the symbols mean. That's still an element.
Are you gonna teach us that this semester?
Are you going to learn that? Yep.
Damn it, I didn't like that.
Yeah.
Writing systems.
Yeah.
It's a language.
Just for the record, that's like my favorite part. So you just like kick me in the nuts.
And also mine, because that's one of my favorite.
Okay. So that is actually really important. Most of the rest of the stuff we teach you, if you're in chemistry, you aren't going to ever deal with again. Okay. This is looking at how structures interact in those molecules. How they interact is pretty important, personally. Okay. And hopefully I'll clarify it for you because they throw in all sorts of loopholes that I think are wrong. Okay. So this would not be a compound, it would be an element. Okay? To make matters worse, because language, we only have one word to represent everything, right?
No.
Like book, text. We use multiple words to reference the same concept. We can also reference as a molecule. A molecule is now, in my opinion, I think it's going to differentiate with compounds because a molecule is more than 2 atoms. A compound is at least 2 elements. Okay? An element is something on the periodic table. An atom is just an individual piece. Okay? So you can reference O2 as a molecule. You shouldn't reference it as a compound. Clear as mud? I usually find this section pretty clear as mud, personally.
You guys remember how we said vocabulary matters and we had to get focusing on that a little bit?
Yeah.
Language matters.
Okay, so let's look at some big classifications. Sorry, did I just walk over you?
No, that actually, I just thought it was really appropriate to go into the language right after the language matters.
So if we go into our language, we will divide up our elements, okay, into certain categories. Why did we divide them up? It helps us to remember and organize and think about them. So we're going to spend a lot of this unit talking about the periodic table and some of its structure. One of the first things that we're going to look at is our difference between metals, metalloids, which we'll temporarily ignore here for a second, and nonmetals. So one of the things embedded in our periodic table is that it allows us to differentiate metals from nonmetals. That's actually kind of neat. Right? And what we found is that when we look at our metals, they're usually solids. When we look at our nonmetals, they're also some gases. Right? That should immediately tend to freak some people out. Why might that freak you out a little bit?
Because there's metal gas.
So there's one assumption. It says most solids, so that means it could be a metal gas. Okay? Yeah, theoretically. These classifications, though, tend to be at standard conditions. So when we typically experience metals and nonmetals, these are the phases that we see. Okay, so when we look at metals, we typically don't see them as gases. Anybody like what I just said? Anybody notice the words? Typically did not see that. Okay, and if anybody says that in any kind of class you're in, you should immediately kind of panic a little bit and then follow it up with,
What do you mean where?
what do you mean? When is it not? Okay? If I'm going to say most are solids, when is it not? Okay? Because for your sake, do you really want to memorize most are solids? It probably makes sense to actually memorize when is it not a solid? Okay? Because if most are something, it's easier to memorize the smaller piece, not the larger piece. Okay? When we move over to the nonmetals, we get most are solids or gases. Well, that's even worse. Okay? It's like saying most of these substances are solids, liquids, or gases. Well, duh. Okay? So we have to be careful with those classifications and realize that what we're trying to do is come up with as best a differentiation as possible. They aren't perfect, but they're pretty close.
Are standard conditions just how like they're naturally found, or?
We will address what standard conditions are, okay, but officially it's 1 atmosphere of pressure, and we're not going to address what standard conditions are, okay, because they don't make sense. When you think about these phases and the periodic table phases, our standard conditions aren't officially standard, but it's room temperature. So anywhere between 20 and 30 degrees Celsius or 60 to 80 degrees Fahrenheit, ballpark, okay? And normal pressure. So you don't feel your ears popping or you don't feel them pressurizing one way or the other.
But I would say the closer I get to 80 degrees, the more liquid and solid I become.
Yeah. Luster. What is luster? Shining. Dull. Lack of shining. So they're kind of trying to set up opposites. And that's one of the interesting things. If we compare metals to nonmetals, for the most part, they are opposites. They have opposite properties. So if you can figure out the properties for metals, you now know all of the properties for nonmetals because it's not that. Okay? And thank you for throwing it in most of the time. Okay? We can get exceptions, and that most of the time is going to become even more irritating for us. So our periodic table allows us to differentiate some of this information. For instance, metals and nonmetals are very clearly outlined on our periodic table. Solids versus gases is also very clearly outlined on our periodic table. The rest of them aren't. Okay? So where is that clear delineation for either of those? We'll call them red, metals and nonmetals, or purple, solids and gases.
Where they are on the periodic table. The higher they
What's
are.
that?
The higher it is, the closer it is to gas.
The higher it is, the closer it is to a gas. Okay? I would argue half right. Okay? Kira was noticing something else?
The staircase.
There's a staircase on the periodic table. If we take a look, starting at boron, you'll see there's that darker line that kind of zigzags down. That staircase is the line between metals and nonmetals. Okay? Well, which side of the line means what?
Left is metals.
Left is metals, right is nonmetals. Do you have to memorize that? Is the staircase on the periodic table?
Yes.
Yes. Name a metal. Iron. What's the symbol for iron? Where is Fe relative to the staircase? Left. You just said iron was a metal to the left of the staircase. Do I need to memorize left of the staircase means metal?
Yeah.
You already kind of had that knowledge built in. That's not an extra thing to memorize. Does that make sense?
What about the bottom two rows? Are those metals?
Metals. Okay. What's to the right of the staircase? Nonmetals. Name a nonmetal. Where's oxygen? Right of the staircase. Okay. So some of that information is already there and you have ways to pull at it. If you didn't have exposure to that information, yes, you might have to add that information in now. But what I'm trying to set up is that you already have some of this pseudo-memorized. Okay. I saw 1, 2, 3.
So then why do we have hydrogen being on the left of the staircase when it's a gas?
Okay, so let's take a look at hydrogen. Hydrogen is a gas.
It's red.
Okay, so which is it? Metal or non-metal? Hydrogen's kind of just an obnoxious exception to a lot of things. Okay, hydrogen, in fact, yeah, I'm just going to do this. because I needed my periodic table. Whoa, come back here. You will see on many periodic tables, usually a solid line differentiating helium and hydrogen from the rest of the periodic table. There are lots of periodic tables that will also show helium here and hydrogen here. Okay? Why?
Is it,
They don't behave like other elements.
Okay? The hydrogen and helium tend to not behave like the other elements. We don't necessarily know the pattern yet for why they're being placed there, but their behavior is a little weird. So we put in that extra thick line to help differentiate it. Okay? We're trying to add some information to help you cognitively understand that they are odd and different. Did our periodic table on the wall do that? No. Okay? Because sometimes chemists just go, you can figure it out. Right? I don't agree with it necessarily, but sometimes that happens. Right? Why would we also potentially put hydrogen on the right-hand side over here?
So that's to the right of the staircase.
So it's to the right of the staircase, and we can say it is very clearly a non-metal. Okay? Why put it in both places, though? There's a pattern and logic behind the periodic table, and it turns out that hydrogen reacts similarly to the elements underneath it. Which elements? Li, Na, K, Rb, Cs. Okay? Which is why it typically gets placed there. 90% of the time, that's how hydrogen acts. Okay? So we've placed it in a location that lends information about how it reacts. That's kind of cool. Why could we also place it over here? Well, while hydrogen is also a nonmetal, guess how else it could also react? F, Cl, Br, and I. Hydrogen has the ability, or a dual ability, to act as both cases. That's why its placement on the periodic table is tricky, and that's why in nicer designed periodic tables, hydrogen and helium are elevated off of the table, because the chemistry of that row is weird. Okay? Kind of makes sense? So, does that address your question, and then by follow-up yours?
Yes.
Yes.
Since there are like so many trends on the periodic table, would you mind that if we like write them down on a periodic table?
I would actually recommend that you write down the trends on the periodic table. I will say there's a lot, and you're probably going to end up writing so much you're going to make the periodic table difficult to interpret.
Can we use that on like the test?
Yes and no. You are not allowed to bring in your version of a periodic table to the test, right? Because there's too much that I would have to go through and look at. But if you look through the slideshow, the very last slide in the slideshow says you should memorize these trends, and when you get the test and a periodic table, what should you do? Write that down on it. Okay? So I want you to have at least held it for long enough to do that and do an interpretation. If I say you can bring it in, I'm not proving that you've held that knowledge at all, because what you could have done is just copied somebody else's. Right? So at least a little bit it's held there. Why am I telling you to memorize that information? On the test, and it's useful to the rest of chemistry. I'm not telling you to memorize random facts for the sake of random facts. I'm telling you because it's useful and applicable further on down the road.
And I really like Ollie's question because it gets at what writing's all about in the sciences. It's you want to find a way to represent the information you need so your brain can focus on harder things. So that hanging on to the trends isn't what your brain has to take its energy on. So I like that as a reason for writing.
So you guys did a good job identifying our metals and nonmetals versus that staircase, but what about our solids versus gases? Black and red?
Yeah, like on the thing.
So some elements are black, some elements are red.
Would it be to the right, and then our gases are red, and then the solids?
So you're applying what was written up here, right? Most of our nonmetals are gases, and notice we see the red ones to the right of that staircase. To Kira's question, meaning you could have a metal be a gas? Yes, but not at normal conditions, because no gas or no metals show up as red. barring that hydrogen issue. Kinda? Okay. So that's useful. You're applying the knowledge you had up here to go to the periodic table. What else could you be using? Alyssa's got an advantage and Alexis has an advantage over everybody else. If we read the fine print says black, solid. Red, gas. Blue, liquid. So I noticed that you picked out red and black, and maybe that was because you had the context of solid gas. It may have also been that you just couldn't see the blue. The blue is not easy to visualize on the periodic table. Okay. On our periodic tables, mercury, Hg, and Br, bromine, are both blue. Those are the only liquids that are standard states. There are some that transition very quickly after that. Okay? But that information is not only encoded in the periodic table, but we had to encode it so much that we had to include a key. Make sure you use legends and keys in pictures. That's why they're there, to help you with that. Make sense? Okay. So, what do you think these are? Solids, liquids, gases? Wrong question. Let's try that again. What do you think these are? Metals or nonmetals?
Are you talking about the picture?
Yeah. First one's dull. So, non-metal. What's the next one? It's a liquid. Could be borderline. Could go either direction. Except if it's mercury, it's a metal, and metals are... You can do better than metal. Shiny. Lustrous. Is that lustrous?
No.
No. So it's probably not mercury. You could probably tell me that one is? Bromine, as a non-metal. Okay? So yeah, these are all non-metals. Okay? Non-metals become trickier to show. So like the next one, that glow, why is it glowing? It's a tube of gas. Would you be able to tell it was a tube of gas? No. So what do? We put 20,000 volts into that tube of gas, and now what does it do? It glows. Okay? Neon signs? Periodic table. It's a tube of gas that we put 20,000 volts into, and it glows. There it goes. Interestingly enough, you glow if you put 20,000 volts into your tube. Don't test it. Okay? Because you also stop. Okay, at that point too. Last one might be familiar to people that have looked at it or seen it before. It's carbon fiber. Okay, so we're looking at carbon fiber being tweaked and manipulated. How about these? They're all shiny, so they must be metals. Except we had 3 sequences of slides, or examples here.
So those are metals.
These are our metalloids. The metalloids become extra tricky because they share the properties of both categories. Right? Based off of pure visual inspection, it's going to be very difficult because you can only see 2 categories. And depending on your metalloid, okay, it could be a solid and dull, in which case it looks like a non-metal. Or it could be a solid and shiny, and it looks like a metal. To really differentiate your metalloids, you would have to dig into those other properties. Those other properties are all things you would have to measure, which means you need experimental equipment. Okay? So a question could be written and say you have a solid that is brittle, conducts heat, has a high density and a low melting point.
That's not metal.
Okay? I said a solid conducts heat, it was brittle, had a high density and a low melting point. We've got properties of both categories. That's a metalloid. Okay? Where are the metalloids going to fall on the periodic table? They have properties of both areas.
Along the staircase.
Along the staircase. That's where our metalloids fall. We're transitioning from metals to nonmetals. In that transition, we're going to get a shared response. Okay? The periodic table that I've got on my slides here isn't the greatest for that because it doesn't have the staircase. And I always screw up the staircase. Okay? but our metalloids are effectively the things on here. If anybody's got the textbook, you can go ahead and take a look at it. Not all of those elements are metalloids. We're done at 45, right?
Yeah.
Okay. Okay, not all of those elements are metalloids. Okay, which would mean to know the metalloids, you would have to memorize them. I think that is an utter waste of time. Okay?
Okay.
If you would like to do so, that is okay, but I will not test you and be like, is germanium a metalloid? Okay? I could ask in a short answer, is germanium a metalloid? And you could be like, well, it is close to that staircase. It could very well be a metalloid. Okay? So you'd have to defend that work. That's not worth it to me. Okay? Next part. We've got 118 elements on our periodic table. The one I've got up on the board doesn't have them all, and it actually hasn't named those higher ones. Okay? How many of those should you know the symbols for? So a couple people have had chemistry classes before. Have they made you memorize all of the elements? Yeah. It's utterly stupid. Okay? Memorization is useful if you continue to use it. Okay? How many of you plan on working on a nuclear submarine? How many of you plan on working at a power plant like Palo Verde? Do you need to know what uranium is? No. It's not worth the time and effort to memorize that symbol. You may already have done so, okay? But that's not worth our effort. Okay? So some elements are of critical importance because you encounter them a lot. And in that circumstance, you should know the name for them. So you do not have to memorize all of them, but what you will have to do is memorize a significant amount of them. If you go into files, I believe it is references, I may have to check, and then elements for memory. I believe it's elements for memory.docx. Okay? That was the list of elements that I was given when I started here. And they said, these are the elements we expect students to have known when they move further up through chemistry. Okay? It's something like 60 elements. Okay? So it's not 118, but it is a lot. Okay? There are a lot of elements on there that I don't think are worth memorizing. Okay? So I went through and also bolded ones that I think are critical. If all you are trying to do is just pass, memorize the bold ones. Okay? If you need something more than passing, memorize that list. Okay? At this stage in the game, all you need is the symbol and the name. We will add more to that as we move through the semester. In fact, this unit will add significantly more to that. Okay, but at this point, that's all you need to memorize. Okay? If you see a number on the periodic table, don't memorize it. Why? It's on the periodic table. Okay? It's bolted up there. We're not taking it down. So if there's a number written up there, you don't have to memorize it. Okay? So name and symbol. Work on that. Okay. So this particular unit, okay, I think does require a lot of memorization. A lot of what we're talking about in this unit is the basics on building upwards. So the communication, the ability to talk about the language. Okay, so because of that, you need to have a lot of that naming down so that we can have proper conversations. Okay. This next unit, or next piece, or chapter, is now talking about how we build our atoms. Okay, we pretty much just said we've got atoms, here's some bulk classifications, now how do we build them? Okay. There's a lot of scientist names, there's a lot of scientist experiments, there's a lot of conclusions that are drawn. I want you to have that content memorized because I think it is valuable. It provides the history behind how the class or the information continued. So when we talk about it in class, you should definitely have that information memorized. As we go through and do it, we'll talk about different ways you could memorize that content.
So say like a scientist has like the theory, would you ask like the test question, like what's the theory of this whoever scientist?
Scientist, yes. Okay. To that end, more than likely what you would say is this scientist completed this experiment. What was the conclusion drawn from that? Okay. So this all starts off with Dalton in early 1800. Okay? And what he went through and did is try to organize our thought. We had a limited amount of elements, and he said, what are elements? And he really kind of defined them, and that's where we're getting our atomic theory. Okay? So he has 5 theories. First theory, an element is composed of tiny, individual, indestructible particles. He's now coined that as an atom. Okay? It's the smallest buildable piece. Okay? Not true. It's false. Early 1800, though. Give him some credit. All atoms of an element are identical and have the same properties. Also false, but again, early 1800. Okay, so what he's working with is the conclusions that he could see. So we could convert oxygen from the air, okay, and react it with hydrogen to make water. It didn't matter where I pulled the oxygen from, but when I reacted it with hydrogen, I could get water every single time. So we noticed that we could exchange those pieces around, okay, and that each atom was roughly the same. Okay? Atoms of different elements combine to form compounds. So I can take oxygen and I can take hydrogen and I can make water. Okay? That's a good theory. Compounds contain atoms in small whole number ratios. Okay? This is kind of a corollary of rule 1. If an atom is indestructible, I can't have a fractional atom in a compound. Okay? So when I build compounds, I'm only adding whole number amounts. Okay? It doesn't have to be 1, it could be 2. H2O. And then atoms can combine in more than one ratio to form different compounds. Okay? I can mix hydrogen with oxygen to make water. It can also make hydrogen peroxide. Water allows me to live. Hydrogen peroxide would kill me very swiftly and painfully. Okay? Same elements, but different ratios changes the properties of the material. Okay? The other thing that I like about this slide in particular is that we get this goofy looking picture on the right. What do you see here? It's the periodic table. And in fact, actually, the top part is the periodic table. The bottom part are the compounds that Dalton was able to identify. Okay? So you could go through based off of the pictures and shapes here and see if you could find water, because I think it's up there. Okay? You have to make some guesswork behind that, but you could probably pull that off. Okay? What do you guys think about this kind of model for describing or using for chemistry? Think about the periodic table we've got right now versus the periodic table he's showing. Okay, a basic version. Why is it basic?
There's not as much.
There's not as many. Okay.
It's like the rough draft.
Okay, we could look at it as a rough draft.
It's a little more image-based.
Image base. Moving pictographic. Thank you. Just wanted to make sure I got that one right. We've got pictographic versus, and unfortunately our periodic table is kind of a mix match of a couple of them, right? Yeah. Okay. Which one would you prefer to work with? Do you want the pictographic or do you want the one that we're using? Why the one that we're using?
More information.
More like defined on what they are. Like you can use the names.
Those symbols don't make sense to you?
Okay.
It's harder to memorize the symbols than just like the name.
Okay, it could be harder to memorize the symbols. Why? You've spent 20 years doing what? Working with language, the English language, and that's the symbol root that we're using here. Okay? Ultimately, a B is just a symbol, just as much as a circle and a dot. Okay? It's just a question of our comfort with those different languages. You've grown very accustomed to the English language symbols. Those are a lot easier to manipulate. Okay? The one I like throwing into this is that if we taught this class with all of these symbols and circles and dots and lines and hashes, what would that look like to you?
Hieroglyphs.
Gibberish. Hieroglyphs is a little bit nicer. More the direction I was going than gibberish. Magic.
An art class?
Okay. An art class. We're looking at the studying of nature, of beauty, and we're trying to represent it as beautifully as possible. Okay. If we have it in this beautiful art form that makes it look like magic, everybody else gets scared and thereby controllable, and we can control all sorts of fun things. Yeah, aren't chemists evil little bastards? that might have been recorded. Hopefully I was far enough away from that.
That's a good way to end the class, though.
Okay? So Dalton tried to put this together and try and organize some of the thoughts. Okay? We'll pick up with, I think, Thompson 100 years later on Thursday.